Hello, this is going to be the Chapter 8 wrap up for our class, where we're going to touch on a procedure for determining if data is normal. So let's pick up where we finished up on Friday in class. And we are in section 8.3, and I was talking about the T interval procedure, which is very analogous to the Z interval procedure. And where we are finishing up is that this procedure is robust to moderate violations of normality assumptions, which was the same thing we said about the Z interval procedure. And what this means is that we can use the same of those when to use rules as we discuss for the Z interval procedure. So let's review what those rules were. The first one, and these rules primarily are dependent on the sample size and the distribution of the random variable of whatever it is you're looking at. So if you have a really small sample size, smaller than 15, then what we really need to be able to apply the interval procedure is that the variable X must be normally distributed or very close, and the data cannot contain outliers. Then if you're in this kind of middle area where you have 15 or up to, but not including 30, so between 15 and 29 data points, then what you need is X can be a little less normal, but still pretty close. It just can't be extremely far from normal. And again, your data cannot contain outliers. And then the third situation is when you have a sample size greater than or equal to 30, where you can pretty much use the procedure regardless of what the underlying distribution looks like. And that's because of the central limit theorem and what the implications of that are on the sampling mean. But if there are outliers, everything can get messed up. So if you do have outliers, you need to do a sensitivity analysis. We talked about this with and without the outliers and see if the results are substantially different. And if they are, then you have to use a different procedure. And at that point, we're going to possibly have time to talk about some of these different procedures. But usually in that case, you would need to probably contact a statistician. And if outliers are present and you have good justifiable reason to remove them, then if your data with the removal of the outliers is one of the previous three situations, then you can apply the Z or T interval procedure. Okay, so we're going to do an example of these when to use rules and specifically determining if data is normally distributed. So this is pickpocket data from the FBI, and it's a sample of 25 offenses where X is the total amount stolen in a day. We're going to assume that the data is given as stated in table 8.6 from your textbook. And we're being asked, what is the 95% confidence interval of the mean amount stolen, or mu? So let's look at that data. So wait, actually, let me go through this. Step 0 is the preliminary analysis. So since we had 25 and that's less than 30, we're going to need to check if the variable X is normally distributed and if there are any outliers. So in order to do this, we're going to use a approach called a normal probability plot. This is also known as a QQ plot. And we skipped over this. This is back coming this when the book covers this, it's in section 6.4. So if you want to look into it or read about it in more depth, you can go there. This is a procedure that works well for small samples. And the big idea behind it is that if X is normally distributed, then the normal probability plot, and we're going to talk about how to construct it, is going to be close to a line. And the terminology that is used is that it's roughly linear. And note that this decision on whether it's roughly linear is subjective and not quantitative. So that's kind of one of the drawbacks of the QQ plot, is that you just have to eyeball it. There's no like measure of how linear it is. It's not like a correlation coefficient is given. You could probably calculate one, which may not be a bad idea, but in and of itself, you just decide if it's roughly linear. And then the idea is if the normal probability plot is not roughly linear, then we assume that the variable x is not normally distributed. Okay, so that's kind of the idea of how it works. We do get a bonus using this approach in that you don't have to do box plots of the data because this technique also can be used to identify outliers. All right, so how do we create a normal probability plot in Excel? So the first thing is we're going to order the data and we're going to get the normal score for each value based on its position. And the position is called the rank. So we will be referring to that. Then we are going to plot the points x, y, and the x coordinate is the observed z-score from the data, and the y coordinate is the theoretical z-score for a normally distributed data. So the idea is, how do these compare? And then we're going to decide if the points are roughly linear or not, and if there are any outliers. Okay. So how do we go about getting this theoretical z-score? I trust you know how to get data and convert it to z-scores already. So the question is, how do we get the theoretical z-score if the data was normally distributed? So that's what we need to kind of do a little bit of a deep dive into that. So the idea behind that is that if the data is ordered, then the position of the data value, its rank, can be treated like a discrete random variable, and we can use the normal approximation and the continuity correction and determine the percentile of what it would be if the data were normal. Okay, so that's a lot to kind of digest. So let's just kind of go through it with an example, which makes all of this much easier to grasp. But basically, if you're given 7 data values and you order them from smallest to largest, and the middle one is the 4th value, right? So then to determine what percentile of the data this is, we're going to use the following. We don't actually look at the value of that 4th one. We actually look at the position and we subtract 0.5. So again, we're going to treat the position as if the ranking are values from a normal distribution. So the 4th data point would be 4 minus 0.5, which is 3.5, and divided by 7, the total number of data points gives us 0.5, or the 50th percentile. So what we would then do is we would do that for each data value. And then if the data were if the data were normally distributed, right? So this is where we're like, okay, this is where we get what is the theoretical value? We can use those percentiles to get the z-score for normally distributed data. So we get the percentile and we plug that into the norm S inverse function in Excel, and we get the we get the quantile out. We get the value on the horizontal axis from the z-score is what we've been calling it. Okay, so let's, before I jump into that, let me go through this in Excel. So here's an Excel spreadsheet, and I'm going to grab the data from the pickpocket example, and it looks like this. So here's the pickpocket data. And then what we want to do is we need to determine each value's rank. So the rank is if we order the data from smallest to biggest. And so you can go ahead and order that and number it, or there's an Excel function that will do that for you. So we would say this is equal to rank dot average. And so then we need the number, which is in this case, the 26. And then what we need is the whole range of numbers that we want to know where in this range of numbers does 26 fall. Actually, this looks like it's been ordered for us, but just in case it wasn't, this is what we could do. And then it says 0 descending or 1 ascending. So we want to know in the ascending order from smallest to biggest. Then I'm going to need this formula for every one of those. So I can just put a function f4 here and turn those into $sign. Okay, so now I can just double click that little green square and it's going to give me the rank of each one of these values. Now, certainly you could sort your data and then just have it start counting for you and give you the count of each position. I just wanted to show you this alternate way because sometimes if you have a lot of data, you just might want to do it this way. All right, so now we want to figure out the percentile on these ranks. So what percentile does this rank the position represent? So we're going to say this is going to equal, and I'm going to use parentheses, the 1 minus the 0.5 for the continuity. And now I'm going to want the count of those data values. So I'm going to say count of these positions. And again, this is just in some ways making this robust to adding data, putting it out of order. These are just some alternative ways that you can do this. But the idea is you have the same result. So this is telling us that the rank 1, when you have 25 data values, represents 2% of your data. So we're going to just go ahead and obtain the percentile. And since for each one of those values, and since the data was already ordered, you can see that we're going from 2% of the data up to 98% of the data. Okay, so now that we have this, we're going to simply get the theoretical normal z-score for these percentiles. So let's just wrap this text. There we go. And so for this, we just simply need to do the norm.s.inverse. So on this value right here. All right, so we see that if this was normally distributed data, the first position would be, or what represents the second percentile is minus a little more than 2 standard deviations away from the mean. And we're going to go ahead and calculate that all the way out. We see that 13th position out of 25 is the halfway point, and that represents 50%, the 50th percentile, which is also the median, and is the normal z-score is, if it's normal, the mean and the median are equal, and so the z-score there is a 0. Okay, so now that we have done all that, we have basically now come up with the theoretical z-scores. So it's one of the coordinates of the xy pair. And to be honest, I think I had said x is the observed and y is the theoretical. It could go the other way. It doesn't really matter. The most important part is that you have constructed the theoretical normal z-scores. And then we want to get the observed z-score. So the observed z-score is, let me just get this to look right. So I'm using Alt-Enter within the cell to get it to return within a cell. Okay, so here, the observed z-score is going to be the value. So we have the value minus the mean of the data. So now we're actually going to be looking at the data values themselves. So I subtract the mean, and then we're going to divide by the standard deviation of this sample data. So we're going to use the dot S here. And we're going to, again, get our data values in here. All right. Now, since we're going to copy this down, I'm going to make sure that these are absolute references using the function F4, just to make these with $signs so that when I copy them, they don't change. Okay, so the observed z-score for that value is minus 1.85. And then I'm just going to double click on this little green button and get all my observed z-scores. Okay, now that I have this data, I can just select both columns of data and go to insert. And I'm going to select a scatter plot right here. Okay. So just to get a little fancy on you, we look at this data and we're like, not sure what exactly I'm looking at. So let's just fix a couple things. So the first thing is, let's give these axes titles. Okay, so the theoretical is the one that ended up on the x-axis, and that's fine. So that's the theoretical. Normal z-score, which is also another more technical term for the z-score, or the value that's on the horizontal axis from a distribution, is the quantile. So that's the quantile. And on the y-axis, we have the observed. So this is coming from our sample z-score, quantile. And then let's just call this what it is, a QQ plot, or a normal probability plot. Okay. Now, I'm going to click on the x-axis. I'm going to right-click it, and I'm going to format this axis. And what I want to do with this axis is I want to decide where it crosses. And I'm going to pick an axis value. And I'm going to go to -3 for a -3 standard deviations, because I know most of my data should be at -3, no more, should be contained within 3 standard deviations. So now I'm going to click on this axis and format this axis. Sorry, I meant to do the y-axis now. Format this axis, and I'm going to go to max axis value, and again I'm going to choose -3. This is just what most people do because of the empirical rule. All right, so now that we sort of move the axis away and we have all our data, we can kind of see what it's doing. What we want to know is if it's on a line or not, roughly linear. So one way that we can do this is we can go up here to this add chart element and come down to this trend line. And on the trend line, we can come down to linear. And so here you see that we have a dotted line showing us that the data does look roughly linear. So now that we've done that, we can feel confident in saying, okay, it appears that we do in fact have a approximately normal distribution of our data. Okay, so let's go back, and now that was step 0, the preliminary data. Okay, so now we've determined that the data is approximately normally distributed and there are no outliers. So we can proceed now to construct the 95% confidence interval. So we want to get the T alpha over 2 comma DF, DF for degrees of freedom. Since we want the 95% confidence interval, alpha is the 1 minus 0.95 or 0.05, and the sample size, which was 25, tells us that degrees of freedom is n-1 or 24. So we're going to put this into the Excel function T inverse 2 tail You can also just use the T inverse function, and then you put the 1 minus alpha over 2 probability in here, which would be 0.975. But with this function, the T inverse 2 tail, we just put the alpha straight in, comma, the degrees of freedom. So doing that in Excel gave me 2.064. Once I have that, then I'm going to go and get from my sample data these values. So let me just show you where that showed up in our data. We didn't actually do it yet. So let's go ahead and go to the data tab and go to data analysis. And we're going to pick descriptive statistics. And you guys did this in CA2, so hopefully you are good with this. So we're going to take this pickpocket data and we're going to say, yes, we have labels, and we're going to put the output somewhere around here. Let's just go here, I guess. Oops. There we go. And I'm going to click on summary statistics and hit OK. Okay. Let me make this left column a little bigger so I can read it. All right. So now we have some values here. We have 513 for the mean, 513.32 for the mean, and we have the standard deviation of 262.23. And these are the two values that we need. Sorry. Let me highlight that. We need that one and this one to create the confidence interval. All right. So coming back over here, we see those two values. So with those two values and the T, the quantile from the T distribution, we can construct our margin of error. So our E is T alpha over 2 comma DF times the sample standard deviation divided by the square root of the sample size. So we saw that that T was a 2064, and we just calculated the sample. Well, we had Excel tell us that the sample standard deviation was this 262.23, and we're going to divide by the square root of the sample size, or we're dividing by the square root of 25. And that comes out to 108.25. All right. And since we want the 95% confidence interval, which is a point estimate plus or minus a margin of error, it is X bar plus or minus the margin of error, or 513.32. Right. So we're going to get this number right here. And that's our point estimate. And we're going to subtract and add this margin of error here. So we end up getting between 405.08 to 621.57. And the interpretation, which is step 3, is that we can be 95% confident that the mean amount mu stolen by pickpocketers in a given day in the United States is between $405.08 and $621.57. Okay, so that concludes that example. Then I wanted to do another example, and this one is regarding U.S. chicken consumption. In this example, a sample of 17 people were randomly selected from the U.S. population and asked to track their chicken consumption for a year in pounds. What is the question that we're trying to answer is, what is the 90% confidence interval of the mean chicken consumption per year in the United States? So we're going to switch over to Excel and look at this problem there. So I'm going to get a whole nother sheet. Let's just call this one pickpocketers. Okay. And we'll add another sheet and we'll call this one chicken consumption. Okay. So this data is in your textbook. And you can get it there. There's 17 values recorded. So here's the chicken that was eaten in pounds. Okay. Now, if you remember, since n equals 17, we actually do need to check if the data is normally distributed and if there are any outliers. Okay, so let's go back and check that now. So we're going to do this using a normal probability plot. So the first thing I can do actually is come over to the pickpocket data, and I'm going to just copy over these 4 columns, the first row from those 4 columns and their headers, just because it makes my life quicker and easier to copy that over. So now I've put this in, and for the rank, I notice that the rank is got this big giant range. So I can hover over the corner until I see not the 4-sided arrow. Let me see if I can get there. That one, the diagonal arrow lets me change the size. Okay, so now I've done that. And then the percentile is going to also tell me the count. And again, I want to hover till I get the diagonal arrow, and then I'll make the red box smaller. Because in a second, I'm going to copy that down, and it's going to tell me what the count is of data, even though I already know it's 17. But if you had a ginormous data set, this would help. So then we want to get the normal distribution, the normal theoretical normal score, which is going to give us that when the percentile is actually real. Right now it's wrong because of all the data below it is off. But I just want to adjust all the formulas before I copy them down. So for the observed z-score, the average, this red box, I need to get that diagonal arrows and shorten up that box. And I'm going to need to do the same for the standard deviation. So I shorten those boxes up, and now I have that in those formulas incorrectly. And now I can actually select all 4 columns. And I believe I might be able to just double click on this little green box. And then I'm able to get all the data quickly calculated for me. Now I want to do that normal probability plot, or the QQ plot, using the z-scores, both the theoretical and the real or observed ones. And I select those 2 columns. I go to insert, and I'm going to go over here to scatter plot. And just like we did a few on the previous example, I'm just going to quickly modify the axes. Oops, let's choose the right thing. Hold on. There we go. Format axes with a axis, that vertical axis crosses at the -3 value. And the y-axis is going to cross at the -3 value as well. Horizontal axis crosses at -3. And then what we observe here, if you notice, is that we have a problem because we have this value down here, and it is very far removed. And so this is that bonus I was talking to you about regarding the QQ plot. Without even changing our axes or going any further, we see that we have a problem. So if you see you have an outlier once you do this plot, why waste time fixing up the graph? At this point, what we really need to do is address that outlier. So we look in our data, and one thing we can do in our data is go ahead and order this data. And maybe the best thing to do would be to order it using the observed z-scores. So using the observed z-score from smallest to largest, I see that my smallest is at -3.24. And that person ate 0 pounds of chicken. So it is very reasonable to assume that person was a vegetarian or just someone who does not eat chicken at all. And it may, in this case, actually be justified in saying we are going to modify how we define our population to be people who eat chicken. So we want to get the average amount of chicken consumed by people who eat chicken versus including vegetarians in that. So as long as we got buy-in from the team or our client or whoever that is, obviously if this is your own business, you can make your own decisions. but normally we work in teams in most cases. So I'm just going to copy this information and I'm going to copy it down here. And I'm going to say with outlier removed, and we're going to proceed without that data. So I'm going to find that first row and I'm just going to delete it out. And I'm going to clear out my annotations here. Okay, so now I'm going to create the same QQ plot all over again by going to insert and to the scatter plot. And now you see that it does appear like the data is let much more in a straight line. I will let you clean this up. I'm going to add the theoretical z-score on the axis and the observed on the y-axis. And then I'm just going to call this the QQ plot. And I'm going to go ahead. You can play around with the x-axis. I'm just going to save time and not do where the axes cross, but we can still go in here and add a linear trend line, which is the main thing we care about. So you can see that this does look linear. So we're going to assume that normality exists. So now that we've done that, what we're going to want to do is go ahead and construct. So that was step 0. And we say, okay, now assuming we modify our population to be the only people who actually eat chicken, now we're going to get the 90% confidence interval. So I'm going to just say the confidence interval percent is going to be 90. And the alpha associated with that is going to be, you can either just do the math in your head, or if you want to do it and have Excel do it for you, it's 1 minus the confidence interval divided by 100 or 0.1. And then we're going to need to get that T sub alpha over 2 value. So the way I'm going to do it is I'm going to use the inverse function with the 2 tails. And I know that for that function, I'm going to need the degrees of freedom. So again, just for demonstration purposes, in case you had a really large data set and you didn't want to actually count them and it took too long to look at the top rank. And because we're going to need it anyway, let's go ahead and get the descriptive stats. As I've told you before, that's kind of a standard thing that you should be doing anyway. So I'm going to go to the data and get the descriptive stats for this. Come down here and choose the data without the outlier. And I'm going to select the location. It's going to be right here, I think. Looks good to me. Everything's fine there. Okay. All right. So now that I have this data, I'm going to go in and get this T inverse 2 tail, where I'm going to put in the alpha that I want, which is 0.1. And then my degrees of freedom is going to be my sample size, which I get from the count, minus 1. Right, and I get a 1.75 T alpha over 2. And from that, then I want to calculate E, the margin of error. So now that we've gotten the alpha, now we're on to, that was step 1. Now step 2 is we get the margin of error and we construct the confidence interval. So remember that it is going to equal the T sub alpha over 2. Let's see if I can move that. Comma, degrees of freedom. And then we're going to multiply that by the S divided by the square root of X. So let's go ahead and do that. So it's going to equal the T alpha over 2, which is comma degrees of freedom. I should have put that in there. And then we're going to multiply that by the sample standard deviation, which is right here. And then we're going to divide that by the square root of the sample size, which is right here. So we put that all together and we get our E. And then we're going to get that 90% confidence interval. And so we're going to have a lower limit to an upper limit. I'm just going to move this down one. So what we're going to do is we're going to say it's going to equal the mean minus the margin of error and up to the mean. Oops, I forgot my equal sign. Equals the mean plus the margin of error. Okay. So if we wanted to round these to 1 decimal, we can just reduce. We use this button to decrease the decimal. It rounds for us. Okay. So we can then interpret this and we can say, okay, interpretation is that we can be 90% confident that the true amount, or we just say the amount of chicken consumed by US chicken eaters is between 62.3 pounds to 72.0 pounds per year. It's a lot of chicken. Okay, so that's where the average amount of chicken is eaten per person per year. And that concludes this wrap up for chapter 8.